The complex number system, basic operations on complex numbers. Hello everybody, and welcome to Middle Third. Today's video is an introduction to the complex numbers as well as the basic operations that we can do on them. Think addition, subtraction, multiplication, and division.
There are a good many similarities between the complex numbers and R2. Both are planes of numbers, and their elements are ordered pairs of coordinates. For R2, we often label the coordinate axes as x and y, and each element in R2 has a unique pair of coordinates. For the complex numbers, the idea is identical, but instead, the coordinate axes are called real and imaginary. The real axis is just the number line, like we're familiar with, but the imaginary axis is a little bit more complex. It has some properties, unlike the real number line, which we'll see in a second.
So, just to reiterate, the elements in the complex plane are ordered pairs of numbers. The first number indicates the real part of the complex number, and the second number indicates the imaginary part of the complex number.
With this established, I want to talk about how to add two numbers in the complex plane. Suppose I had two numbers in the complex plane, p and q. How would we add them together? Well, it turns out that addition in the complex plane is identical to addition in R2. Think of p and q as vectors in the complex plane, and add them together just like you would add vectors in R2. You add vectors by the parallelogram rule, which I show here. P plus q is the resultant of the parallelogram rule for these two complex vectors. Perhaps you can see that when we do addition on complex numbers, or vectors in general, we add component-wise. First we add the real parts of both numbers together, and then we add the complex parts of both numbers together.
So, the upshot from this is that addition, and therefore subtraction, in the complex plane is identical to addition and subtraction in R2. But how about multiplication? How would we multiply two numbers in the complex plane? R2 does not have a well agreed upon idea of multiplication. Sure, R2 has things like the dot product, the cross product, the exterior product, the atomar product, among others. And while the complex plane also has these products, it does have a well agreed upon idea of multiplication. So if I have a complex number, a comma b, and multiply it by another number, c comma d, I get a complex number in the form ac minus bd for the real part, and bc plus ad for the imaginary part.
Now hang on, this is an odd way to multiply numbers regardless of what system you are in. Where does this come from? The reason why is that although we can represent complex numbers as an ordered pair, there's another way to represent them that is more suggestive when it comes to multiplying complex numbers. Instead of representing complex numbers as an ordered pair, we can represent them in this sort of vector notation that is similar to what you might have seen in multivariate calculus. If we look at the complex plane, more specifically its axes, we can make unit vectors on these axes. On the real axis, the unit vector will be 1, and on the imaginary axis, the unit vector will be labeled I. If we think about R2 again, suppose we had a number in R2, xy. Well, in unit vector notation, xy can be represented as x hat plus y hat. The complex plane acts exactly the same, but it uses different unit vectors that I've just mentioned. If I have a number ab, I can represent it as a 1 hat plus b I hat. Now typically, we just drop the 1 hat since it's equal to 1. And we also drop the I hat notation and just let it be I. Again, to reiterate, a, as we said, is the real part of the complex number, while b is the imaginary part of the number because it has the extra I term on the end of it.
So, if we want to multiply two complex numbers, a plus bi and c plus di, we multiply them just by distributing terms. Now, I claim that I squared is really just -1. And that's a big claim, but I'll justify it at the end of this video. The expression we have can be simplified by combining like terms, and notice, if we convert this notation back into our ordered pair notation, we get the exact same thing as what I defined complex multiplication to be. AC minus BD is the real part, and BC plus AD is the imaginary part.
So, for example, if I have a complex number p at point -3, -1, and a complex number q at a point 2, 1, then using our formula for multiplication and doing some arithmetic, we can see that p times q is equal to -5, -5. For addition, we saw that adding two numbers has a very intuitive geometrical meaning. We're using the parallelogram rule and adding vectors head to tail. What's the geometric interpretation for multiplication? Is there one? The answer is yes, there is, but we'll have to wait to a later video to see what it is.
What about dividing complex numbers? This is a little bit more difficult and requires a little bit of work on our part to see. Before we talk about dividing, I want to talk about something known as the complex conjugate. Suppose I have some complex number z in the plane. The complex conjugate, which we will denote as z star, is just the flip of z over the real axis. Essentially, we just reverse the sign on the imaginary part. That's it. That's all the complex conjugate is.
But we can use the complex conjugate to understand division. If I take any old complex number, call it z, and I multiply it by its complex conjugate, I see that the result is a squared plus b squared. Now, if I do some algebra and move the complex conjugate to the other side, then take the reciprocal of both sides, I see that the reciprocal of a complex number is equal to its conjugate over a squared plus b squared. Doing some algebra, I can split up this into a real and a complex part. Now, if I multiply both sides by another complex number, say c plus di, if I do some simplification and some algebra, I now have the formula for dividing a complex number by another complex number. Notice again, the division of two complex numbers is indeed a complex number itself. It has a real part and an imaginary part.
So there we have it. We have shown all the basic operations for complex numbers: addition, subtraction, multiplication, and division. One of the last things I want to introduce for the complex numbers is the idea of value, or rather, the lack thereof. In the real number system, we make comparisons about two numbers all the time. Some numbers are bigger than others. 1 is less than or equal to 8. 5 is always greater than 4. E is greater than pi.
But what about complex numbers? Does a complex number, say 5 plus 3i, greater than or smaller than 4 plus 7i? It isn't immediately obvious. 5 is greater than 4, so the left number's real part is greater, but 7i is greater than 3i, so the right number's imaginary part is greater. So how do we make a comparison? Well, it turns out that this is another similarity between complex plane and R2. In R2, there is no idea of a vector being smaller or bigger than another vector. The vector 1, 2 is neither greater nor smaller than 4, -3. There's just no way to make this comparison.
This is because C and R2 are what is known as unordered fields, which means you can't order the numbers that they contain in a specific way. The real numbers are an ordered field. They have an underlying structure that says some numbers are bigger than others. However, coming to the complex number system, not all hope is lost. We can still compare complex numbers in the sense that we can compare two numbers' magnitudes, or lengths.
Suppose we had a complex number z. The magnitude of z, which we would denote with double bars, is just the adding of the real part and the imaginary part in quadrature. Hopefully you can see that this idea of magnitude is exactly the same as the idea of magnitude of a vector in R2. The magnitude, geometrically, is the total distance the complex number is from the origin. So, although we cannot compare complex numbers directly, we can compare their magnitudes, or lengths.
Finally, you may have noticed that when I talked about the complex numbers in the last section, I mentioned that they were a field, a special kind of field, namely one that is unordered. But what is a field exactly? A field is a set in which all the basic operations of addition, subtraction, multiplication, and division are defined and act in a predictable and reasonable way. This is a crude definition, and the actual definition is a bit more complex. But notably, if you want to check if a set with certain operations is a field, you can do it by checking that all of the field axioms hold. Notice that these axioms are properties of numbers that we take for granted. Associativity, commutativity, inverses are all things that we use in everyday mathematics but don't give much thought to. When introducing the complex number system, these ideas are no longer so trivial. For example, is it true that every complex number has an inverse? We will explore this in another video and prove that complex numbers are indeed a field.
I mentioned earlier something that you should take for granted, namely that I squared is equal to -1. Where does this come from? The complex numbers really begin to take shape in the 15th to 16th centuries, when mathematicians wanted to find solutions to polynomial equations, namely finding the roots of cubic and quartic polynomials. However, imaginary numbers pop up in even the simplest of quadratic equations. Take x squared plus 1. Say we wanted to find the roots of this polynomial, and by that I mean, where does this polynomial cross the x-axis? You can clearly see that it doesn't, but nonetheless, when we use the quadratic formula to solve this equation for x, we see that the solution to our question is when x is equal to positive or negative square root of -1. Maybe the alarm bells are going off here, because we know that there's no real number whose square is negative. But unfortunately, this idea of roots of a polynomial depending on square roots of negative numbers is unavoidable in an infinite amount of polynomial equations. Simply put, to this equation, and many others, there is no real, tangible solution to the equation. A solution does exist, but the solution is a number that we're not familiar with. According to René Descartes, the solution to the polynomial equations like these are sometimes only imaginary. We take this square root of -1 and we give it its own name, I. And this is the same I that shows up in our complex number system. It's the complex unit. Hence, if we take the square of I, we see that I squared is -1.